Okay, so in section 5.21 here and the next section 5.22, he's going to mention the functions that we might be using later on. So let's take a look at this list. So here's a function, and this is the absolute value of x. So absolute value of -4 gives you 4. And the next one is the square root of x. Square root of 25 gives you 5. Since that's the same as doing this, you can do it this way, or you can do it square root. Ceiling x, smallest integer not less than x. So the smallest integer not less than this number is 4. And floor x, the largest integer not greater than x. So that would be 3. So it should not be greater than x, but it's the largest one of those. And next one is trunk x, truncation. In x, integer formed by truncating values in x towards 0. So you just this becomes get rid of the 9, and what do you get? You get 5. Round x digits n. Round x to the specified number of decimal places. So round this to 2 digits. So we want to get rid of the 5. So what do? When we round, if it's 5 or above, we raise this up 1, so this becomes 8. Okay, sign if. Round x to the specified number of significant, I guess that means significant, sorry, of significant digits. So I'm not sure about this actually, but it looks like what it does is, since it says 2 digits, we only want to have, here we have 4 digits, not decimal digits, but digits in any sense. We have 4, so we want to just make it 2 digits, so it rounds it to 2 digits, which means that this, because this is 7, this becomes 5. So we get 3.5. And cosine, sine, and tangent, arc sine, arc cosine, sorry, arc sine, arc tangent, hyperbolic cosine, these are just functions. I don't know if we're going to need them. I'm surprised we're going to need them, but I don't think we will. But anyway, those. And then there's log of x base n, and log of x, which is the natural log. That means normally we would call that ln of x. I don't know why they don't call it ln of x. And log 10 of x is log base 10 of x. Here. Okay? We have those. And this is the exponential function, e. Okay, then he gives us a few comments here. He says data transformation is one of the primary uses of these functions. So take data and you transform them. You might have a whole lot of data, whole vector of data, and you transform it by raising each item to the power of e, or to that, how do I say it? Raising e to each of those powers. Now, why would you want to do that? Who knows? Can't think of any reason, but you might. And now, one thing he does mention is that, for example, you often transform positively skewed variables such as income. Let me just show you what they mean by that. So here we have a picture of incomes and the number of people that have these incomes. So this is called positively skewed because we say it has a long tail to the right. Now if it looked like just the opposite, looked like for example like this, and then went up and then down, so it would have a long tail to the left, that would be called negatively skewed. Okay, but this is positively skewed, and usually like income will look like that. In other words, you'll have a few people that have really high incomes. Okay, so he says in that case, what we'll do with this income variable is take the log of it and then do some, maybe look for relationships between that and something else, because that's what we're interested in, looking for relationships between income and other variables. Like if someone has more income, do they buy more cars? If someone has more income, are they happier? And so on. We're looking for relationships between income and other variables. So, but first he says he'll probably take the log because of the shape of this and what logs do. If you remember what logs do, they make large numbers kind of not, in a sense, not as large. But anyway, we'll often take the log of positively skewed data. That's what he says. So he says, for example, you can often transform positively skewed variables such as income to a log scale before further analysis. And one more thing he says is the examples in this table above apply mathematical functions to scalars. So all the examples he gave here, we said the cosine of 2. This wasn't a vector, right? This was just a single number. When the functions are applied to numeric vectors, or even matrices, or data frames, they operate on each individual value. For example, the square root of this gives you this, right? The square root of 4, 16, and 25 are 2, 4, and 5, respectively. Okay, next we'll do statistical functions.